Welcome back to the world of physics. Today to start class, we're going to do a warm-up problem. That warm-up problem is displayed on the board now. You can see it describes a stunt woman who's wearing a jetpack that has two rockets, but the two rockets are misaligned. One rocket accelerates her up at 4.5 meters per second. The other rocket accelerates her at 5.8 meters per second, but at a 28-degree angle to the right of the other rocket. Find her resultant acceleration, and once you've done that, if the rockets burn for 3.8 seconds, find how far she will go while the rockets are on. It takes 6 minutes to solve this problem, and at the end of 6 minutes, I will show you a solution to this problem. Press pause now and take the 6 minutes to solve this problem individually. All right, your 6 minutes are up. Let's take a look at how this solution should be done. First off, these two accelerations, the 4.5 meter per second acceleration and the 5.8 meter per second acceleration, are happening simultaneously to the same object, but they are not in the same direction. One of them is 28 degrees to the right of the other. That calls for a vector diagram, which is why you can see the ruler and the protractor have popped up. So I'm going to make a scale. And it makes sense in this case to make a scale so that 1 meter per second in the problem is represented by 1 centimeter of distance when we make the vectors a certain length. Make that a little bigger so you can see it. So there's my scale. Now, if I draw a little sketch of what's about to happen, I know that there's a 4.5 meter per second acceleration that's up. There's another acceleration that's at a 28 degree angle to the right. So if this is 0, this would be 90. So 28 would be somewhere in there, and it's a little bit bigger acceleration, so that might be a little longer. So I know my resultant is going to end up looking something like that. But in order to do this well, I need to break out my ruler and make good measurements. So I'm going to extend the page a little bit so I have a little bit more space, and start by putting my ruler straight up. And I'll make the first vector. Remember, it's 4.5 meters per second, so I'll draw that vector 4.5 centimeters long. There we go. And now I'll take my ruler out of the picture, and in order to get these lined up, you could do one of a couple of different things. The first thing you could do is put the vertex of the protractor, that is right here, on the tip of the first vector, and measure a 28 degree angle from there. That 28 degree angle from there would be right there. And so I can draw my next vector towards that, and I will have built, since this is 0 degrees, I will have built a vector that is already in the right direction. So they're already tip to tail and in the right direction, and I can simply add them. So I'm going to do that now. So we'll go ahead and make that little mark. That little mark is going to be right at 28 degrees. There we go. And I'll get the protractor out of the way. Line up the ruler. With the edge just like that. And now I'll be able to make another vector that represents the 5.8 meter per second acceleration. I'll make that 5.8 centimeters long. And we're good. Now I'll move the ruler out of the way, turn it so that we can go from the tail of the first vector to the head of the last vector and draw in a resultant. Resultant vector represents the actual acceleration of this stunt woman. Since both rockets are firing simultaneously, she really has both accelerations at the same time. Now you can see that when I measure how long it is from right here to right here, it's a little longer than 10 centimeters. I have 10.1 centimeters. So if it's 10.1 centimeters, according to my scale, that would equal 10.1 meters per second. That will be her acceleration because both rockets are firing at the same time. Of course, we want to label these vectors whenever we do a diagram. So this would be 5.8 meters per second. That vector, put that label next to the vector that's 28 degrees to the right. And we want to label the vector that was straight up. and that was 4.5 meters per second. And now we can simply label our resultant vector. And that resultant vector is 10.1 meters per second. Now, because this is a vector problem, we do need to make sure that we measure the direction of that vector. So I'm going to put my protractor straight up and put the vertex right on the tail of the first vector. So I am doing that. I'm going to move this up a little bit so you can see it better. I'm putting the vertex right here, and that way I can go out here and read the direction that the acceleration vector that results from the 4.5 and 5.8 meter per second vector, this 10.1 meter per second vector. I can read the angle of that, and it looks like it's about 16 degrees. So the actual acceleration is not simply, whoa, that's a big protractor. It's not simply 10.1 meters per second. It is 10.1 meters per second, 16 degrees right from vertical, since we were referencing, when we put our protractor on the first vector, 0 degrees, which is right here, was in line with straight up. So that 16-degree angle is measured from vertical. So now we've got the acceleration of the stunt woman due to both rockets firing simultaneously. That brings us to the second part of this question. So we found her resultant acceleration. And now what we're looking for is the answer to this question. If the rockets burn for 3.8 seconds, how far will she go? Now, in order to do that, we actually need to use this acceleration. That acceleration is what is actually happening to her because she is attached to both rockets simultaneously. So we do not use the 4.5, we do not use the 5.8, and we certainly wouldn't use their algebraic sum. We wouldn't use 4.5 plus 5.8 is 10.3, because that acceleration would only happen if both rockets had been aligned and been pointing the same direction. What I want to make sure you understand about a problem like this is that once we're done with the vector, the resultant from the vector, if that's what's actually happening, and in this case it is, can be used. Now we can solve for the distance, because we know that distance is half of the acceleration times the time squared, and we were given the time. The rockets are going to burn for 3.8 seconds, and we have the acceleration from the vector diagram. So we are going to do d equals 1/2 at squared. Now the problem doesn't say so, but it's reasonable that if she's wearing a jetpack and she starts to accelerate up, it's reasonable to assume she might have been on the ground to start with, so we're going to assume that VI was 0 here. So in for acceleration, we're going to put the 10.1 meters per second, and in for the time, we'll put in that 3.8 seconds. So when we substitute that in, that's going to look like d equals 1/2 of 10.1 meters per second times the time squared, where the time is that 3.8 seconds. Notice that when we square that, not only does the 3.8 get squared, but also the seconds get squared. Oops, didn't need to move that. The seconds get squared as well. It's the seconds getting squared as we square the time in the equation that cancels out the per second in the acceleration, so that only meters remain, so that we now know the distance that the stunt woman will travel while the rockets were on. When we put those numbers into our calculator, what we find is that the distance is 72.922 meters, and we only have, two significant figures in this time. So 72, we can keep those two digits. The next digit though is 0.9, so we're going to round up. So that becomes for us not 72.9, but now just 73 meters. So that is our answer of how far she goes. And if we had asked for her displacement instead of just how far, we could also add on that she will end up being 16 degrees from vertical, since she's accelerating in that direction, she's going to end up moving in that direction since her original speed was 0. What I really want you to take from this problem, let's zoom out and look at the whole page, is that if we have a problem where two accelerations are happening simultaneously to an object, we can use a vector problem to take those two accelerations and find her actual acceleration. But then once we do that, we can take that actual acceleration and use it to find out other things about her motion using the kinematic equations that we've been using in the past. So now we have a problem. Now we can have problems where we can use our skills with vector addition to find out more information, to be able to then use our skills with kinematic equations to find out even more information. So look for these kind of compound problems where you'll need a vector diagram to get started, and then you'll go back to using the answer to that vector diagram to find out more with kinematic equations. All right, let's start today's lesson. So today's lesson is on interval problems. Interval problems do not involve vectors. What they involve is breaking a problem up into pieces. So in an interval problem, what we have is all of our equations that we've used before. So these are simply all the kinematic equations, Vf minus Vi over t, Vf squared minus Vi squared over 2d, average speed times time is distance, and the equation that we just used, Vit plus half at squared is distance, and its cousin, Vft minus half at squared, is distance. All of those equations can be used in any problem as long as the acceleration is uniform during that time. So if an object accelerates at one rate for one period of time and then has a different acceleration, what we're going to do is just break that problem up into two pieces. Let me show you an example on the next page. So here we've got some screenshots of a movie where you can see Mr. Lowry right here, and he is dropping a bowling ball. Now from the moment he lets it go, when it was in his hands here, until it hits Mr. Bradley's hands down here, the reason that it would be falling and gaining speed along the way would be because of gravity. And so we would expect the acceleration during this time to simply be ag. Now, once he starts catching it, so as soon as the ball hits his hands at this point, then we would expect from here to as he moves his hands to catch it, because of course you can't just stop a bowling ball. It's pretty massive, so it's hard to stop. So as the ball moves downward while it's in his hands, Mr. Bradley would actually have to push up on the ball to make it lose its downward speed. So the acceleration is not caused by gravity anymore. The acceleration of the ball would be the acceleration because of the force that Bradley puts on the ball up. You might label that if you wanted to put a subscript right here next to the acceleration, you might put acceleration while stopping or acceleration while caught. Now, we actually made a VT graph of what's going on by clicking in each frame as the ball dropped, and not surprisingly, the spacing got bigger and bigger as it dropped, and then as he caught it, the spacing got smaller and smaller because he was slowing the ball down. Now, when we take a look at that VT graph, and I'm going to zoom in on it here on the next page, what we see is that the trend is that the velocity is negative the entire time, and it's increasing in speed. This is -1, and then this is -3, so it's actually going faster, but in the negative direction. That's during this part of the fall from here to here. And then we see that that speed starts decreasing towards 0 as it's being caught. So that speed is decreasing when Bradley is pushing up on the ball during the catch. Well, what we simply do is just break the problem into two parts. Since we have one acceleration as it's falling and a different acceleration as it's being caught, we break the problem right when the acceleration changes. So let's go to the next slide so we can see the numbers a little bit better. All right, so here's a closer look at that graph of the bowling ball's motion. And you can see that what's on the y-axis of this graph is the y velocity in meters per second. So that's how fast it's moving down. And again, you can see that the speed at the start is -1 meters per second. So we started clicking on it after Mr. Lowry let it go. And you may recall when we studied velocity time graphs that the slope of a velocity time graph is the speed of the slope of a velocity time graph is the acceleration of the object. So let's remind ourselves of that the slope of VT graphs, those are equal to the acceleration of the object. And we can see that, zoom that up a little bit. We can see it. We can see then that the slope is fairly consistent from here to here, and it should be because it's falling due to gravity the entire time. This point right here where the slope changes and becomes positive is the point right when he caught it, when he first started touching it, because that's when Mr. Bradley is pushing up. So we would expect a positive acceleration, and that's why the slope becomes positive rather than negative. Hey, not surprisingly, take a look at what the slope is as it was falling. You can see that it's -9.653 meters per second. Air resistance did not affect the bowling ball very much, and so the acceleration was very close to what we would expect it to be, -9.796 meters per second, since we're in Denver. But when we found the slope as he was catching it, you can see the speed is decreasing, getting smaller. Remember, we're looking at negative velocities here, so the speed was about -4 meters per second when he first touched it, and by the time the end of this graph, we've reached the end of this graph, he slowed it down to about -1.4 meters per second. So we've got a case where we've got negative velocities that are decreasing because of a positive acceleration since he's pushing up. And that's going to be true for every what we call fall and stop problem. As an object falls, the acceleration and velocity would be negative because gravity pulls down, and we make up positive in up and down problems. And then when he catches it, or when something lands on the ground, the acceleration will be positive. That's why the object loses its negative velocity, because it's being pushed up at landing. Now when we look at the actual slope of the VT graph, which again is the acceleration, we find that it's a positive 13.65 meters per second. The acceleration is actually slightly larger than it was as it was falling. It makes sense because it stopped in a shorter period of time and it stopped more quickly. Because it stopped more quickly, that means that it had a larger acceleration. That means Bradley's pretty strong. He was pushing up on it much harder than gravity was pulling down on the ball in order to cause that acceleration. That's not uncommon either. That's why landing hurts so much more than falling, because the acceleration at the bottom is usually bigger than it was on the way down. So how would we deal with that if we were asked a word problem? Well, let's go to the next page and see. So if we were asked a word problem like this, a bowling ball is dropped and Mr. Bradley catches it after it falls freely for 0.34 seconds. The ball comes to a stop in his hands as it moves down 0.482 meters. We could find the final velocity of the ball just before Mr. Bradley catches it, and then we could figure out what's going on with the acceleration of the ball once it's in his hand. Let's draw a diagram to make sure we understand what's going on in the first place. So there's going to be a period of time and a distance that the ball travels where it is simply falling. And because it's falling, we want to make sure we label that and treat that separately from what's going to happen afterwards. So what's going to happen afterwards, and I'll often just draw a dashed line to kind of remind myself that, hey, the problem broke right there into two pieces. So the next little chunk is what's going to happen as Bradley catches it. So we want to make sure that we break the problem up into two parts. Because all of our equations, now I'm flipping back all the way to the first slide. Because all of our equations, not that slide, this slide, there we go. Because all of our equations, remember, only work if we have uniform acceleration. That means that in a problem like this, a classic fall and stop problem, where there was one acceleration for one period of time, and then at the moment where Bradley touched it, its acceleration changed. We have to break the problem up and we can use our kinematic equations here and use AG as the acceleration, and then we could use our kinematics equations here and figure out what the motion is going to be like during that time. And the thing that links it, here's the key. If you learn nothing else today, here's the key. When you recognize that you've got an interval problem because the motion of the ball changes because of some new reason, in this case, Bradley catching it. Right at that moment, look, the speed is known. That speed, if it's not known, you could calculate it, for the fall was about 3.8 meters per second on this graph. If we know that speed, we can use that as the final velocity for what happened first. But it's the initial velocity for what happens next. So that means we can simply, if we can find the speed at that moment, we know a piece of information about the first interval and the second interval, and it happens to be the same piece of information. Because that's at the end of the first interval, we would call it VF, but because that speed is at the start of the second interval, we would use it as VI. So you'll hear me say lots when we're solving interval problems, just reminding you to find VF of one interval because that's VI of the next interval. And that's why you can see we've set this up to find VF, the final velocity of the ball, just before Mr. Bradley catches it. That would be right here in the problem. That becomes VI for the next interval, so that then we could find the acceleration of the ball as it comes to rest in Mr. Bradley's hand. So let's go about doing that. All right, so if we're going to do that, we got to recognize what do we know about the fall. Well, what we have about the fall is that AG equals negative 9.81, because we don't really know where Mr. Bradley was in this. We're just going to use our average, 9.81 meters per second per second. All right. Recognizing that G should be a subscript, so I'll make it so. There we go. We've also got VI is 0. Since we know that the initial velocity is 0, because he simply dropped it, that allows us to use simplified equations. That's useful, so 0 meters per second. And we know that it fell freely for 0.34 seconds. So the time between when he dropped it, where it was right here, to when it was first touched, then that's 0.34 seconds, so we can put that in. So t equals 0.34 seconds. Now when we do that, now we've got 3 pieces of information. So the correct equation that we could select out of our kinematic equations would be the final velocity is going to be equal to A times T plus VI. So make that a little bit bigger and put some subscripts on it. So VF equals AT plus VI. And since we have all 3 pieces of information, A times T and VI, we can plug them in and find the final speed at the end of that fall. So let's do that now. So we're going to plug in. It's equal to negative 9.81 meters per second times that time, 0.34 seconds, plus the original speed, which was 0. And when we calculate that out, we get negative 3.3354 meters per second. We get, sorry about that, we get negative 3.334 meters per second. The fact that it's negative shouldn't bother us. It is falling down. At that point, it would have a speed that's downward. In fact, it should be negative. Now, the key here is recognizing that that velocity is the final speed at this moment right here, which means it's the initial speed for the motion where he's catching it. And the acceleration changes as soon as Bradley touches the ball. So none of the information that we knew from before, the original speed of the ball or AG or time, really matters during this interval. The piece of information that matters during the catch is the final speed at the end of the fall. So now we can use this piece of information as VI for the catch. Right, now that we know VF for the fall, that tells us what VI for the catch is. Of course, since he caught it, kind of intuitively know that if you catch something, it stops. So VF for the catch part would simply be 0 meters per second. Well, that gives us two pieces of information now that we can use to calculate the acceleration of the bowling ball while Bradley caught it. We've got the velocity when it first touched his hand. Again, although that was VF for the fall, we'd be calling it VI now for the catch. We also have another piece of information from the problem. The information we have from the problem is that it fell down, or excuse me, it moved down 0.482 meters as he caught it. Now, we have to be careful here. We just say it moves down. That doesn't mean that it fell down. It's not falling anymore, he's catching it. And that's why it's so important to draw the diagram and label what's going on in the problem during each interval. So we can take that 0.482 meters, we can bring that down and recognize that that's the distance it moved while it was in his hand down here. So one more thing, it moved down. We actually need to make that distance negative when we use it in equations so that we calculate the acceleration correctly. So now we've got three pieces of information, VI, VF, and distance while he was catching it. Since they all pertain to when he was catching it, now we can calculate the acceleration of the ball as he was catching it, as it came to rest in Mr. Bradley's hand. So to do that, we need to pick an equation. Well, with VI, VF, and D, the equation that we would choose would be this one. Acceleration equals VF squared minus VI squared over 2 times the distance. So we plug in some values there. Zoom out so you can see this a little bit better. We're going to plug in some values there. That would be equal to, I'm going to copy that again and paste it, and now we'll just put in the actual values. So ungroup this. Oh, that's just a picture of it. Never mind, we can't put it in. We put in VF squared, so that would be 0 squared minus, all right, sorry for the interruption, minus, careful here, the negative does not cancel out due to that minus. So we got to make sure that we go back in here, be minus the negative 3.3354 meters per second. That quantity gets squared. Make this a little bit bigger so you can see it. Now be careful here when you do calculate it. That negative here gets canceled by the square because negative times a negative is a positive. But this negative does not. So the top of our fraction is going to be negative. Now the bottom of our fraction, put that underneath here, would be 2 times the distance. And when we put 2 times the distance underneath there, what we'd be putting is 2 times that negative 0.482 meters. Now I want you to notice something here. When we do this calculation then, this negative right here is going to get canceled out because that value is squared. This negative is part of the equation and is not canceled simply because VI is squared. This negative, however, cancels out this negative, so we are actually going to end up with a positive answer. That makes sense. If the ball fell and then was caught, he'd have to be pushing up to make it stop. So the acceleration should be positive. Now when we calculate that value, what we get is 11.54035 meters per second per second. Notice that when we do the calculation here, it ends up in meters per second, and the reason it ends up in that unit is because we have meters per second squared on the top, so the equivalent of that would be meters squared per second squared, and then we're dividing on the bottom by just meters, so that cancels out the square here, and we're left with acceleration units. So it's positive because you'd be pushing up, and it's in meters per second because that's what the units work out to. The key to all of this is recognizing that the speed at the end of the fall right here is critical. because it is also the speed at the beginning of the catch. Even if we hadn't asked you to do part A, in an interval problem like this, you need to do part A to be able to do part B, excuse me. Find the speed where the interval changes, and you'll be on your way to solving the interval problem correctly. All right, let's do some follow-up questions and see how well you understand the concept of intervals and where to break a problem up into parts. So here we've got a clicker problem. What I'd like you to do with this clicker problem is read it and then take a minute to discuss with the person next to you and decide upon an answer. So a rocket-powered cart is launched in the physics room. It starts from rest, gaining speed at a rate of 18 meters per second squared as the rockets fire. The cart moves 4.1 meters while the rockets burn. After the rocket motors run out of fuel, the cart coasts along the floor for 0.53 seconds before running into a student's backpack. The rocket cart came to rest in a time of 0.0165 seconds while in contact with the backpack. Into how many intervals should this problem be broken? So press pause on the video, take 1 minute to discuss this with your neighbor, and decide 1, 2, 3, 4, 5, or 6 or 7 intervals, or perhaps you just don't know, and then I'll follow up with the answer in just a moment. Press pause now and take 1 minute to discuss the answer. Okay, we're back. I hope that you decided upon 3 intervals. 3 intervals is the correct amount of intervals to break this problem up, and let's diagram why. If we haven't convinced you to start diagramming problems yet, I hope we do soon. So here's how I would think about this problem. You've got a rocket cart, and the rocket cart has on it some flames, of course, right? Where the rocket fuel is going to be burned and the exhaust comes out. Now, that rocket is going to come out and it's going to go a certain distance from rest while the rockets are burning, right? So I might call this rockets on, right? Then we'd break the problem up into a new chunk. We'd break that problem up because the problem says that the rocket motors run out of fuel and then the cart coasts. So the next part I might actually just call coasting. And at that point, I break the problem up again because then the problem describes that it runs into a student's backpack. So when it runs into the student's backpack, since the problem describes it runs in the student's backpack at that point, then that's kind of a crash. I might label this next interval as crashing. And from the problem, what I would know is the VI of the rockets on, it's 0, starting from rest. I'd know the acceleration as the rockets were firing, so that'd be the acceleration during this time. So I'd put that 18 meters per second of acceleration here while the rockets are on. Since I've got VI and the acceleration, if I had one, and I've got the distance, the 4.1 meters, would also be during the rockets on part. Those 3 pieces of information would allow me right here to find VF. VF of the rockets on would be VI of the coasting, and since I've got the time of the coasting, I'd put that in here. Now if it's coasting, its acceleration might be close to 0, so I might just use that velocity and time to calculate how far it goes to the end. And then it comes to rest in this much time. That time actually belongs in this interval. And I could use the speed it had when it hit the backpack and the fact that VF is 0 after it's done running into the backpack to calculate things about the motion in the backpack. We would simply use all these equations. I'm flipping back to the first slide. We'd use all these equations, but we would use them in each of these intervals separately. So this really just breaks into 3 problems. All right, let's take a look at this one. A woman is trapped on the 5th floor of a building when a fire starts on the lower floor. The fire department sets up a large inflatable bag on the street below, and the woman falls from her balcony to safety. She falls 13.2 meters before contacting the bag, then moves another 1.9 meters as she comes to rest. What was her velocity in meters per second when she first impacted the bag? So individually take 3 minutes to solve for her velocity as she just touched the bag after her 13.2 meter fall. Pause the video now. All right, we're back. So let's see how we would solve this problem. First off, recognize that this distance doesn't matter if you're looking for her velocity at the end of the bag. You don't have enough information while she's actually hitting the bag to solve her speed right when she first hit it. What you do have is that she falls from her balcony. That tells you that for the fall part of this, the VI would be 0, and she's going to fall from the 5th floor down. And then that's where she's actually going to hit the bag. So I'd break this problem up right when she hits the bag. The bag will push her up, and in the meantime, she was falling down due to gravity. So we've got negative 9.81 meters per second of acceleration as she's falling. And we've also got VI is 0, and we've also got that this distance is 13.2 meters. That allows us to choose the equation that VF is the square root of 2 times the acceleration times the distance. We're plugging in 2 times negative 9.81 meters per second times, careful here, negative 13.2 meters. And the reason that has to be negative is because she fell down that far. Those two negatives cancel, and that allows us to actually solve for an answer. And that answer is 16.08478, which we would call about 16. This is negative meters per second on impact. Now we just had to use logic to make it negative, because remember, whenever we take a square root, the answer is either plus or minus, but we can reason through that she'd be falling down when she hit the bag. Now, because we found the speed right at the moment where her acceleration would change. She'd be falling beforehand, and once she hits the bag would push up on her, so her acceleration will be different. Now we can answer another question about it. So let's flip to the next question. A woman is trapped on the 5th floor of a building when a fire starts on a lower floor. The fire department sets up a large inflatable bag on the street below, and the woman falls from her balcony to safety. She falls 13.2 meters before contacting the bag, then moves another 1.9 meters as she comes to rest. What's her acceleration in meters per second? Now be careful, this is as she impacts the bag. That's a new problem. So we've got her fall, and then we've got when she hits the bag. We want to find her acceleration as she stops very quickly while hitting the bag. So VI is 0 up here. We know now that the VF of the fall is that 16.08478 meters per second. Go back to the unrounded number since we're going to use it for more calculation. That, though, is VI for hitting the bag. That's the key to this whole lesson. That if you can find the speed right at the moment where the acceleration changes, you've got VF of the interval that happened beforehand, in this case a fall, and you've got VF of the interval that happens afterwards, in this case landing in the bag. VF of landing on the bag is 0, and from the problem we know that she moved 1.9 meters downward, so we'd make it negative as she hit the bag. Now then, we could go ahead and solve for her acceleration with acceleration is VF squared minus VI squared over 2D. When we do that, we find the solution to be 68.08. Because there's more in my calculator, meters per second. It ends up being positive because the distance is negative, and that cancels out the negative in the equation. We'd round that for purposes of sig figs to 68 meters per second. That's still a pretty big acceleration. This definitely wouldn't feel good, but it's well below the 150 meters per second that causes concussions, and so she might be a little sore, but she's not going to be broken, and that's the point of landing on an airbag rather than on the concrete. All right, we are done with the lecture. The most important thing is recognize when you've got one interval of motion where there's an acceleration of some value and an object is moving, and then something happens in the problems to tell you that the acceleration is now some other value. Find VF at the stop at the end of one interval. That is VI for what happens next. That speed can be used with your kinematic equations in either interval. Try intervals 1 through 5, applying this logic. Good luck.